Okay, so let's continue with the Colpitts. So we are looking at the tapped capacitor and the tapped inductor structures, right? So remember, so this one, the tapped capacitor gives you the Colpitts and the tapped inductor gives you the Hartleys. So, ouch. Draw it in a better way. Okay, so this is the Colpitts. This will be the Hartleys. Oh yeah, I think L1, L2 is better maybe. Okay, and so today what we, of course, the we also saw that the frequency of oscillation. Right, that's 1 over root LC equivalent. So what we'll do is we'll analyze this guy, the Colpitts oscillator today. So the way we'll do it is, so we know that the oscillator is a large signal system. So can one of you turn on this fan? Just turn on everything. Yeah. Okay. So we know that the oscillator is a large signal system. Okay. So because the oscillation amplitude is going to be in probably several hundreds of millivolts to probably a volt, and could be higher. So what we'll do first is we'll find out the large signal transconductance of the transistor. Okay. In something similar to Colpitts in an oscillator configuration. Then we'll use that in the Colpitts and then find out, okay, conditions, I mean find out what the circuit looks like and so on. So first let's take a transistor. So let's say there is some oscillation at the gate. Okay, let's call this C. We'll call this V1. Okay, and let's say the current through the transistor is ID, and the bias current is I0, or I bias is better because we are going to analyze the Fourier series, so it's easier to use I0, I1 for that. Okay, so what we are going to assume is, we are going to assume V0 is large, as I mentioned. Okay, we are going to assume omega naught is large, and in a minute you will see why we are assuming these things. And C1 is some very low impedance at omega naught. Okay. So let's say you're going to plot the voltages as a function of time. Okay. So let's say at the gate the voltage looks like this. Okay. So we'll say this is t equals 0. Okay. What is V1 going to look like? So what will happen is, So transistor will definitely be on. So C1 will get charged along with V0. But then what happens is, when the gate voltage goes down, the transistor will get cut off, right? And the capacitor charge stays constant, and it will slowly start getting discharged through the bias current. So this one turns off, and this one will start, the current source will start discharging the capacitor till the next cycle. Okay? Till the next cycle when it turns off, and so on. Okay, so this will happen every cycle. So if you plot ID, what is that going to look like? So for most of the time, the current is off, the transistor is actually off. So the current is going to be 0 for most of the time, except you are going to get pulses of current, which coincide with the peaks of the sinusoid, the cosinusoid, right? Is that clear to everyone? Okay. So now what we'll do is, so now we know, we don't know the approximate, we don't know what form the signal will take, the current signal, but we can actually find out turns out we can actually find out the fundamental and the bias and so on. Okay. Okay, so what we are going to do is, we are going to write it as a Fourier series. Okay. What is I0? I0 is obviously I bias. It has to be, right? Because the capacitor cannot carry any DC current. So if you go down, so the average is I bias. Okay. Next, let's calculate the fundamental component. What is that? 2 by T. This is the fundamental component, right? But what do we know? We know that ID of T exists only at the peaks of the sinusoid, and at this point, the cosine value you can approximate it to be 1. Okay, so because it's just going to conduct for a very narrow sliver of time around the peak. So this is approximately ID of T dt. Okay. What is this? This is nothing but, right, I bias is nothing but 1 over T integral 0 to T ID of T dt. So this is nothing but twice the bias current. Is that clear to everyone? Okay. How about higher components? So what we are going to assume is, there is some network there which is going to filter out the other components. So we are going to assume that only the fundamental component of current creates a large enough voltage to affect the circuit. Okay, all rest of the current gets filtered out, rest of the harmonics. Okay. So what is the large signal transconductance of the first harmonic? Right? Okay. This is the large signal transconductance. So remember, so you have for a long channel transistor, the GM was 2 others over VD-SAT, right? For a short channel transistor, remember that ID was mu n. Remember this? So your GM is nothing but I bias over VD-SAT for a transistor which is completely in the short channel, right? But remember, the actual expression for the current is we actually had L times EC in parallel with VGS minus VT. Remember that? So the actual, even though we know that the transistor is going to be somewhat in short channel, but it's not going to be in deep, short channel effects, right? Where it's going to show deep short channel behavior. So it's going to be somewhere in between. So we know that the GM is going to lie somewhere in between these two extremes. Okay? So this is the expression for the ratio of the two GMs, the large signal to the small signal GM. Okay? And just remember, this is actually an approximation. Okay? So for example, if you plot this guy as a function of time, it's going to look like this. It's a 1 over V1 curve. Right? So let's say let's plot this guy. It's going to look like a 1 over V1 curve. Okay? However, in reality, the actual curve is probably going to look something like this. And it's going to reach 1. We know that. So this approximation is valid for large signals but not for small signals. Okay? So now we are in a position to redraw the equivalent circuit for the Colpitts in terms of its large signal transconductance. Okay? Okay, so you have your minus GM times V1 correct? This is what goes to the source. Remember that this is the source. So your current is actually, gate is connected to bias, which is signal ground. So it's actually minus GM times V1. Correct? Sorry. What? Okay, what about this? Yes. That is voltage at the gate. Okay, so this is not exactly the Colpitts. This we are just trying to find out the large signal transconductance of the transistor when you have a large capacitance at the source. Okay, so in reality this is not the Colpitts. Okay, when you go to the Colpitts, you are going to use this large signal transconductance that you have derived here and then use it to design the Colpitts. Okay, so this is not necessarily the Colpitts. This is just any circuit. Okay, any such circuit.
But when you calculate the large signal transmitted, you take the gate source voltage.
Yes, Yeah, in that case, you will only have a sinusoid here. Effectively, you will still have a signal component across the gate source, right? Even though gate is grounded, you will still have a signal component. Okay? No. This is just V0. Just V0. So if this is just V0, V1 will follow V0 because you are assuming Vt is very small compared to V0. Okay? So to first order, it will follow V0 and then it won't discharge. It will discharge very slowly because you are assuming that I bias is discharging, the capacitance is very large. That's what you are assuming. Okay? So we are going to do the same analysis for this guy. So this is, let's say this was some voltage V1, and so you have minus GM V1 here. So this you can redraw it slightly differently. Okay. So the input impedance looking in at the source is 1 over GM, right? Is that clear? So you're just redrawing the same thing, except that you're decoupling this and sending it to the source. Okay? So effectively what you can do is, you can split this as this guy. You can split it like this, right? This is nothing but a 1 over GM impedance, right? It's minus GM V1 connected to V1, and the current is obviously the opposite direction from what you would expect from an impedance, right? So this is 1 over GM, and then you have the rest of the circuit. Okay? And of course, the output of the tank is V out, this point. The voltage which is fed back is 1 over n times V out, right? We saw that last week. This is your equivalent turns ratio. Okay? So effectively you can think of it like this. If assuming that there is no loading, right? That the turns ratio is very large, you can think of the equivalent circuit something like this. Okay, and of course you have 1 over GM on the other side, right, where this is an ideal transformer. Oops, sorry. So you can again redraw the equivalent circuit. and actually okay, just reflect the impedance back to the primary side, and of course this again this is nothing but the series equivalent, right, or C1 C2 over C1 plus C2. So resonance happens at, we know this, we just saw that before, but this is again from the large signal model. What is V out? What is this guy? Right? Remember that the large signal GM is 2I by S over V naught, right? And the gate source is V naught cos omega naught t. So the actual current, signal current there is 2I by S cos omega naught t. Okay? So what is the output amplitude? So it's the fundamental peak component 2I by S times RP in parallel with n square over GM. Is that clear? So let's just simplify this a little bit. Okay, 2I by S RP over 1 plus RP GM over n squared. Okay, but of course remember that GM actually depends on V out through n, through 1 over n. So we want to make it independent. We want to get an independent expression, because remember that GM is 2I by S over V naught, and you know V naught is 1 over n times V out, right? Right? GM is 2I by S over V1. V1 is nothing but V out over N. Is that clear? Doesn't like it. Okay. Okay. This is your output amplitude. Okay, you design with a certain turns ratio, you can find out what your output amplitude is. Is that clear? Okay. Of course, the last thing to remember, for startup, so let's say the oscillator is starting up, you should remember that use the small signal GM, not the large signal GM. Okay, just make sure for your small signal loop gain. Okay. Actually, before we go there, I wanted to cover a couple of other things. I don't know if I have it here. Yes. Okay. I do. So what are the different performance metrics of the VCO? Right? First one, obviously the center frequency. Okay? So let's say remember that you are going to use some kind of DC control voltage to tune the oscillator. Okay, so let's say it has some frequency profile, something like that. Okay, so you want to be somewhere there. Okay, that's your center frequency of the oscillator. What is your tuning range? It's F2 minus F1, that is the overall frequency change at the output over the center frequency in percentage. Okay. How do you tune the oscillator? So remember, we looked at the MOS varactor and the diode varactor. Okay, and remember that both of them is a two-terminal device. Both of them are two-terminal devices. Okay, so what you are going to do is put two of them together in a differential configuration. Okay, so it's going to look something like this. Okay, is that clear to everyone? So the control voltage goes to the central point. Okay, one more thing to remember. Okay, what is the difference between this and doing this? What is the difference between these two cases, and which one would you choose and why? Any ideas? Okay, obviously the first thing is in one case you may have a curve like that, in the other case you may have a curve like this for the frequency versus control voltage, but that's not a big problem at all. Okay, you can just change the feedback sign of the PLL into which the VCO is locked, so that's not a problem. Okay, so what other problems can you think of? Sorry? Okay, what kind of loading? Why should there be a DC loading? Actually, so remember, Okay, so what do you have here? You have the source to bulk and drain to bulk capacitances. You have the diode, okay, which causes that source to bulk and drain to bulk capacitances. And that capacitance is going to have a certain Q. Okay, typically, so what happens in this case? In this case, you are directly connecting your VCO to that node. So effectively, any parasitic capacitance you have is going to shift your oscillation frequency and reduce your tuning range. Okay, so that is the first one against this guy. Whereas this guy is much better. You are actually connecting this to signal ground, right? That's much better. The second thing, if you look at the Qs, this side you only have the gate. The Q of the gate is very high. Okay, whereas on this side, the Q of the diodes and the parasitic capacitances is much lower. Okay, so you want to do this, the first one, not the second one, because unnecessarily you are hurting your Q and hurting your, in the end, your noise, your amplitude, everything. Okay, what else do we have? VCO gain. So it's usually represented by KVCO. So it's nothing but the slope of your frequency versus control voltage curve. Okay, it's usually represented in megahertz per volt. Is that clear? Obviously, power consumption. That's, I don't have to tell you about that. What else? So you need to quantify the supply rejection. Okay, in the case of the VCO, that's called supply pushing. So what happens is, so let's say the VCO has a certain power supply and that power supply has some disturbance on it. Okay, what you'll see is it will end up in as spurs and what is called phase noise. We'll probably get to that at the end of today's class, I think. Okay, or maybe not. Phase noise. Okay, if you don't get to it today, we'll definitely get to it on Wednesday. Okay, so what happens? Spurs, we already looked at it last time. So if you have some kind of periodic tone on the supply, okay, let's say the periodic tone is at 10 megahertz, okay, and let's say the VCO is operating at 900 megahertz. What you'll see is, even though it's only at 1 megahertz, at the VCO output, you'll end up seeing it at 901 and 899 megahertz. Okay, so the tone on the supply gets upconverted, and similarly, if you have some noise, that also gets upconverted to the oscillation frequency. Okay, so this is another metric. What else? Pulling, of course. Okay, so don't even need to mention that because we talked about it last time, right? When we talked about transmitters, about how you can have either electromagnetic or substrate coupled pulling. Okay, and of course the last one is phase noise. We'll get to it next class. I mean, it's not the last one, it should be right at the top, but I put it at the end because we're going to do it later. Okay, okay, so since we have 10 minutes remaining, let's look at quadrature generation. Okay, so what are the different ways of generating quadrature? We looked at least one of them last time when we discussed the transmitters, right? Sorry. right? We looked at one of these. So in reality you can have a true polyphase filter. So you need to have, to do that you need to have some kind of buffering. Okay, definitely you cannot directly load the oscillator like that. Okay, so first of all you always want to have buffers, so that is one important thing. Okay, one of the specs you will see is you will have to drive some load. Typically it could be the mixer load, it could be something else. Okay, and you will always have some buffering, so that, and quite often you might have to drive a long line to end up at the mixer. Okay, so you will always want to have buffers. Okay, and then so you would have the polyphase filter, and this will give you 0. This will be your I and Q differential. Okay. Okay. Then what else? What other ways do you know? So of course the polyphase filter is going to look like this. Okay. So on one side, actually let me go to the next page. Okay, it's going to look something like this. Let's call this. If you look at the two phase signal coming in, you'd have something like this. Okay, so the things to remember: if you want to drive these kind of resistive loads, you need power. Okay, which means good buffering. Otherwise, the VCOQ will go down. Right? What else? So the phase error, you want ideally 0, 90, 180, 270, but you're going to have some kind of phase error at the output depending on the mismatch between RC, between the different RCs. Okay, so that's going to limit your phase error. And of course, the one thing you have to keep in mind with respect to power is, if you want to reduce the power of the drive, you need to increase your R. You want to make it, try to make it as capacitive as possible, which means if you increase your R, your capacitance will reduce. Okay, because your RC decides what frequency of you're operating at, and if you decrease your C, you become more sensitive to parasitics. Okay, you have to keep that in mind. Okay, so and as you go to higher and higher frequencies, this becomes a problem, because both R and C become small, first of all. Okay, and now you want to make your R as large as possible, so your capacitance becomes really small. Okay, what is the other way of quadrature generation? Okay, so you can have a frequency divider. Okay, that automatically gives you 270. So you just take two D flip flops. So you're basically, to make a divider, you're going to make a counter which counts up to 2. Okay. So all you're going to do is take, let's do it in a different way. Okay, so this is going to give you 0 and 180 degrees, 270 degrees and 90 degrees. Of course, you need your input frequencies, right? Okay, so the clock inputs get the VCO signals. So obviously the VCO needs to be twice the frequency of your LO frequency. Okay, so if you are designing a transceiver which is going to operate at, let's say, 1 gigahertz, your VCO will have to operate at 2 gigahertz at least. Okay, so the only thing to remember is, keep in mind is, now in terms of phasor and everything else, this divider, this synchronous divider is going to be good. Okay, however, as the frequency goes higher and higher, you are going to burn more and more power, okay, in the divider. So the third option is to design a quadrature VCO. So what you are going to do is, you are going to take two VCOs, okay, this I minus, so let's say this so you're going to have some coupling ports. You're going to have the output that we already had for the oscillator. Now you're going to have two more input ports, which are the coupling ports. Okay, so one set of outputs you're going to directly connect up, the other ones you're going to flip them and connect them. So effectively, you're taking two identical oscillators, you're going to couple them in such a way such that they are going to oscillate in quadrature. Is that clear to everyone? Okay, how do you do it? So there are many ways of doing this quadrature coupling. So one way is to do this. Okay, let me go to the next page. One way to do is parallel coupling, which is so we have two identical oscillators. Okay, what we are going to do is create something like this. Okay, we had the original oscillator, we are creating two more sets of input ports. Okay, so what, let's say the outputs of the oscillators are AB and CD. So the way we are going to connect the couplings is, on one oscillator the outputs C and D are going to go directly, on the other one we are going to take the output and then flip them over and then connect them. Okay, and this will give you your quadrature. Now what I want you to do is, as a homework, I want you to analyze how this works. Okay, right now I have not explained how it works, how the coupling happens. One easy way to look at it is, assume what happens. Okay, so assume some waveforms, okay, at A, B, C and D. Of course A and B and C and D as pairs are going to be differential, assume that. Then what I want you to do is assume that A, B and C, D are exactly in phase and exactly out of phase. Okay, I want you to see what happens. Okay, I want you to see what happens to each oscillator and through the coupling ports. Okay, you can have series coupling. So what you can do is, take the same guy, except actually I want to move this guy also. That's okay. You can couple the oscillator outputs through series. Okay, and this series coupling, you can interchange the positions of the cross coupled transistors and the series transistors. That has been done also. Okay, what else is possible? Harmonic injection. Okay, so what you are relying upon, remember that the output voltage of the oscillator is purely sinusoidal. Okay, especially the differential voltage is going to have the component which you need, plus maybe the third, fifth and so on. Okay, but each side of the oscillator as well as the common mode nodes are all going to have the even harmonics. Okay, because remember, the oscillator still has some operation in the even harmonic, even though it's undesired. What you see as a voltage will just be the odd harmonic. Okay, so what you will see is, at the common mode node, for example here, so you are going to have some, okay, so at this node you are going to have some second harmonic component. Okay, and similarly you are going to have some second harmonic current. Okay, so now what you are going to do is exploit the second harmonics in the circuit to couple the two oscillators, because what happens is, if you have an oscillator which has some signals at the output, you can show that the second harmonic has a particular phase relationship with the fundamental. Okay, so what you are going to do is, you can exploit that, because if two oscillators are going to be in quadrature, that means that the second harmonics are also going to have some phase relationship, because each one has a phase relationship with its own output. So there are many ways to do this. So for example, some people have done this. Okay, that's a capacitive coupling. Okay, so what happens is, you'll have some kind of second harmonic current till it gets coupled. Okay, okay, some people have done this. Okay, and of course you need to have some kind of biasing scheme. Transformer coupling. Okay, there are actually many ways to do this. Okay, so now in this case you are actually exploiting the phase relationship between the currents. In the case of the capacitive coupling, we are exploiting the voltages. Okay. Okay, so let's stop here. I think we have pretty much we have pretty much exhausted everything. So, and of course, I think I may have forgotten to mention, you can actually couple for example, since you have a second harmonic at the common source node, you can actually couple to the current source itself instead of doing through a transformer. You can take the voltages at this point and feed it to the current sources, cross couple it. You can do that also. There are many ways to do it. Okay? Okay, so let's stop here and we'll continue on Wednesday. And I definitely promise phase noise.